All right. So welcome to our last day of class before spring break. So we have spring break next week, no class meetings. Um, the plan for today is to finish up section 6.3 on multiplying polynomials. Just another problem or so there. Discuss some special products, section 6.4. That's a fairly short section, so that won't take long. And then mainly focus the rest of our time on dividing monomials, 6.5, and then start 6.6, and we but we will leave the latter part of 6.6 until after break. So I think it's good to maybe split that up over break. We'll talk a little bit about dividing monomials and polynomials today. You'll have a week or so over break to, take a glance at that a couple more times. Then we come back from break. We'll finish up the section on dividing polynomials and move on from there. One note about break, I strongly recommend against, I know it's really tempting to do, but I strongly recommend against just kind of checking out for an entire, what would amount to about a week and a half from, tomorrow, from Friday through the following, or through 2 Tuesdays from then. I think it's really tough to come back after taking that much time away from something like math, where we're building up concepts the whole semester, and come back and really get your momentum back up, really get back into the swing of things super quickly for the Unit 2 exam and for the final. So I would recommend over spring break, take a couple of days, maybe 2 days, where you set aside a half an hour, maybe an hour each of those 2 days, and just touch base with the material. Just, work through some practice problems, maybe work ahead on a little bit of homework or something, or look through the second part of 6.6 or whatever you would like to do, but just, to keep in touch with the material a little bit here and there. I'm not saying to take, 20 hours over break or something and go crazy with it, but take, again, a couple of days, maybe half an hour, work through some practice problems, work through some homework, some old homework problems or something, just kind of keep in touch with the material so that it's not so much to get started back with right before finals. And that's probably a good idea for most of your courses, but especially in math, because everything builds on each other so linearly in such a comprehensive fashion. I think it's really important to do that. So, and the quote of the day today, heading into spring break, is by a guy, Peter Arve, the co-founder of Prezi, the I guess PowerPoint-like kind of software. And his quote, "The concept of always being reachable makes us present nowhere." So I think that's, particularly maybe apt for going into spring break, maybe try to disconnect and just have an enjoyable week. Keep safe, enjoy your week, de-stress a little bit, and then come back ready for finals. Okay. I guess I said come back ready for finals. It's not that finals are right when we come back, but come back ready to ramp up to finals. Okay, so last time we had talked about multiplying a binomial by a binomial, and we also talked about multiplying binomials by polynomials with 3 or more terms. And we're just going to go through a couple more problems in that section. We'll work through a couple of problems in the worksheet, and then we'll move on to the next couple of sections. So here I see I have a binomial, polynomial with 2 terms, multiplied by another binomial. And I think for this one, maybe I'll use the FOIL method, just because I tend to use the distributive property. But just as a reminder that we can always use the FOIL method for binomial times binomial. And we just want to be very careful about the minus sign here. So again, my preference is the distributive property because I think it generalizes very well, and I think it's easier to handle minuses and negatives. The FOIL method can sometimes trip you up a little bit there, and it only applies to binomial times binomial unless you really force the issue. But the FOIL method was we multiply the first terms, the first term in each binomial. We multiply the outer terms. Being super careful that -3, that minus comes along with the 3. We multiply the inner terms. And then we multiply the last terms. So this is inner and then last. And again, with the last terms, being super careful to bring that minus sign along. And we can come through and simplify. I'll do the simplification a little more quickly. We multiply the constants to get 6. And then we get x to the 4th, same base, we add the powers. We get a minus 9x cubed plus 2x squared. And then minus 3x. We look through the polynomial that we ended up with. We look for any like terms, any terms that have the same variable to the same power. I don't see any. I see the same variable x everywhere, but the powers are 4, 3, 2, and 1 in each of the terms. So no like terms here. So that's the simplest form we can get.
Excuse me?
Yep. Yeah.
You lost me on the way from the distributed, like where it was all the numbers, and then you just ended up with 4.
So this step.
Yeah, you lost. I don't. You lost me there. I'm not
Yeah, I did go a
exactly
little
sure.
quicker than because we had gone through a few of these last time. I went a little quicker there. Was it this term?
Yeah, I don't know how. I j- See, the problem that I have is that this is like the point in algebra where my brain is just not putting the it's not putting the how to do together. So I
Yeah.
I'm just a little confused. My apologies.
No,
So
no.
why
Yeah.
did it shift from cubed to the power of 4?
Yeah, let's break out this first term here.
I would really appreciate
Yeah,
that.
yeah.
Thank you so much.
Yeah, definitely. Yeah, so we want to do this multiplication. And I think one of the things with algebra is moving from, say, arithmetic to algebra, we're generalizing a lot of the concepts in arithmetic. So when we're working with multiplying numbers, we know that like 4 times 3 equals 3 times 4. We have the commutative property. We know that we have an associative property like 4 times 3 times 2. We can multiply the 4 times 3 first and then by the 2, or the 4 times parentheses 3 times 2. We can kind of rearrange parentheses. We can rearrange order. That's the associative and commutative properties. So we're taking kind of we're zooming out a little bit in a sense and saying, okay, we know that ultimately this x, or this x cubed, and this x just represents a number. So those properties still apply, even though we don't explicitly see the number here. So we can, for instance, say, okay, we could think of this as 3 times x cubed times 2 times x. We can basically just get rid of those parentheses and just write out the string of multiplications. We also have the commutative property, which means we can rearrange the order. So for instance, I could swap the x cubed times 2 to be a 2 times x cubed. I can regroup however is convenient to me. So I could group together like that instead. And I see that 3 times 2 is 6. And now I have to figure out what is x cubed times x. And we had a property that if we have the same base, if we have two factors, two things multiplied together, and they have the same base, we add the powers. So if we have a to the power b times a to the power c, that's a to the power b plus c. And so that was a property that we saw. We kind of said, well, if b and c are integers, that's a to the b is like multiplying a by itself b times. And then a to the c is like multiplying a by itself c times. So overall, we're just multiplying a by itself, b times plus c times, or b plus c times. So that's a to the power b plus c. So this was a property of exponents that we had in a previous lecture. And we see that that does apply here. X to the third times, well, this x is really an x to the first. And we see we have the same base. We add the exponents, that's x to the 3 plus 1, or x to the fourth power. And we would do something similar for these next 3 terms also. This next term doesn't have any second factor with x's in it, so the x cubed just kind of comes down. And then the 3 times minus 3, that gives me the minus 9. This third term, we could rewrite x times 2 times x as 2 times x times x. The constant 2 just comes down, and then x times x, again, that's x to the first times x to the first. So we add the powers to get x squared. And then the x times minus 3, we just write that in a more convenient notation as a minus 3x. But I think this first term here is really kind of the crux of this step. If you can, get that first term, then the other ones are a bit easier than the first term. Yeah, but that's a good question, though. Yeah, in algebra, we're leaning much more heavily on some of these properties that we have, like multiplying bases of the different powers, or multiplying the power to a power rule where we multiply the powers. So we're leaning much more heavily on these properties, which we've kind of generalized from the arithmetic rules. So we're using some of these exponent properties, also some things like associativity, commutativity, things like that as well.
Can you like zoom out so I can screenshot this?
Yeah.
Okay.
Yeah, sure.
It's just a lot of numbers and
Yeah,
things
yeah.
to work with. It's a little overwhelming.
Yeah, and I think it's one of those things too that, the first 3 or 5 problems that you work through are going to be really difficult. You're going to make mistakes. You're going to say, wait, what was that property? And have to, look this up somewhere in your notes or something. Or, and then, problem 6 through 10 will go a little more smoothly. And then problems 10 through 15, you're like, oh, okay, this is starting to make sense. The properties you need are a little more at your fingertips. You're used to working with them. And, by the time you've done 20 problems or something like that, this might mean, another section or two after, the sections build on each other. So a problem like this might be implicit in a future problem after you've worked with it for a while. It's like, oh, okay, I understand that now. So I think that's part of it too, is that, it does just take some time to get, in a sense, like fluent with it, just same as learning a language. Like, at first you're like stumbling through, like, wait, what's that conjugation, or how does the past tense work or something? But eventually you get to the point where it's something closer to second nature to be able to do those constructions. Okay, so let's look at this one. And since we did the last one with the FOIL method, let's do this one with the distributive property. And remember, the way that I do a distributive property in this kind of context is I kind of think of this almost as if it's a monomial, as if it's one thing. This parentheses 3ab minus 2 and parentheses, I think of that as like its own unit, its own thing. And here I have a binomial. So I'm going to distribute this thing onto the first term of the binomial, the 2a, and onto the second term, the b. So I have the thing I'm distributing, whatever it is. At this point, I don't care what it is. It's just that thing, parentheses 3ab minus 2, multiplying 2a. I have a plus, and then my 3ab minus 2, the thing I'm distributing, times b. I did my distributive property once, but now I see I have an opportunity to do distributive property again. Here, I can right distribute that 2a into the 3ab and onto the minus 2. And similarly, I could distribute this b into the 3ab and into the minus 2. So I'm going to use my distributive property, two more times here. I used it once in this step, and then I'm going to distribute 2 more times. I should end up with 4 terms from this. So I have 3ab times 2a. That's the distributing the 2a onto the 3ab minus 2 times 2a. These are connected with a plus. I have 3ab times b and minus 2b. And again, I'm going to go through a similar process. Let's break out one of these and work through it carefully, and then the others we'll go through a little more quickly. So I can think of 3ab times 2a. These are all just multiplied together, so I can multiply them in whatever order I want, or I could just get rid of these parentheses. I can use commutative property to shift around these factors. So I have 3 times 2 times a times b. And then I can regroup them. I have the constants I can group together. The factors of a I could group together, and then the factor of b I'll just leave a 1 at the end there. 3 times 2 is 6. A times a is a squared. Remember, this would be a to the first times a to the first. Same base, we add the powers. And then times b. So this first term would turn into 6a squared b. And we could go through a similar process for each of the following terms. So minus 4a, 2 times 2 is 4, and a, so that wasn't too bad. We just multiplied the constants. 3ab times b, the only constant I see is 3. The only factor of a I see is just that one factor of a. And then b times b, just like down here, that's b to the first times b to the first, or b squared. And then lastly, minus 2b, just minus 2b. I look for any common, any like terms, anything I can combine together. This has a squared times b. I don't see any other terms with a squared times b. This term has just an a, no other terms with just an a. AB squared, no other like terms. Just the b, no other like terms. So this is as simple as we can get it. Okay, let's jump over here and oh, I want to do one more problem. We had worked through all of our binomial times binomial problems last time, but this is the one that we'll work through on the worksheet, a binomial times a three-term polynomial. And we actually worked through one of these as well last week in lecture and one in the worksheet, but we'll do one more for practice. So again, because I have a three-term polynomial here, I can't really use FOIL. I could force the issue if I really wanted to, but it would be kind of awkward to use FOIL. The distributive property is the better way to go. So I'm going to take this same structure here, where I kind of treated one of the bits as if it were a monomial being distributed into a binomial. I'm going to do a similar thing down here. And it doesn't much matter which one we pick to be the somewhat like a monomial and which one we pick to be somewhat like a binomial. So I'll just pretend that this is the monomial, that it's one unit, parentheses, 1 minus y, and parentheses, and that's the piece that I'm going to distribute through to the polynomial. So this 1 minus y is going to distribute through to the first term, the 3y squared, to the second term, the plus y, and to the third term, the minus 4. So 1 minus y distributing to the 3y squared. I have a plus, a 1 minus y times y, a minus 1 minus y times 4, same distributive property that we used up above. We just have 3 terms in our polynomial now instead of 2 terms in the binomial. And then just like above, we're going to use distributive property again in each of these terms. So we're going to use distributive property 3 more times to distribute the, for instance, the 3y squared term into the 1 minus y, the y into the 1 minus y, and the 4 into the 1 minus y. So if I look at my first distributive property here, I get 1 times 3y squared minus y times 3y squared. So that all came from that bit. My second distributive property, plus 1 times y. And then I get minus y times y. So this stuff came from that middle term up above. And then here I have to be careful. I have a minus 1 minus y times 4. I know that when I have a minus something and I'm trying to do a distributive property, it's really easy for me to mess that up. So I'm going to make a minor edit to this before I do my distributive property. Let's see if my tech will work with me today. Let's see. Oh, not quite. I missed the parentheses there. Instead of 1 minus y times 4, I'm going to bring that 4 out in front, make it 4 times 1 minus y. So just change the order that those two were multiplied. And then instead of minus 4 times 1 minus y, move this over a tad more. I'm going to make this plus negative 4 times 1 minus y. So I used the commutative property to change the order that 1 minus y and 4 were multiplied. And then I used the fact that minus something is plus negative of that thing. That's really what it means to be minus something. And now I can distribute. And my negative sign here, it naturally comes along with the distributive property, with the piece that I'm distributing. Now, when you get used to doing these, if you want to kind of skip a step, as long as you're super careful with the negatives, you can, do this in one step, not do this rearrangement. But again, because it's somewhat tricky to do, because it's easy to make a mistake, I would recommend going through these extra couple of steps. It does take, a little bit more thought to kind of prepare things before the next step, but I think it's time that's well spent. So now I'm ready to distribute here. I have a negative 4 times 1. And then I have negative 4 times minus y. So I could do something like negative 4 times minus y with a plus. I might have realized, at this step before I did this, that the negatives are going to cancel. So you could have not written the negatives, that would be fine. But just to write everything out explicitly, we'll write negative 4 times negative y. Okay, let's simplify now. 1 times 3y squared is just 3y squared. Up here I have y times 3y squared. Again, I can rearrange. I see that y times y squared, same base, I add the exponents, that's going to be a y cubed. So I get a minus 3y cubed. From here, I just get a plus y. From here, a minus y squared. Negative 4 times 1 is negative 4, plus a negative 4 is just minus 4. And then negative 4 times negative y, negative times negative is a positive, and I get plus 4y. And now I see that I do have some like terms. I have some y squareds that can combine together. My y cubed, I don't see any other y cubed terms, and I don't see any other constant terms. But I do also have 2y to the first terms that can combine together. So maybe what I'll do is I'll reorder things to put those terms closer together, and then I'll do the simplification. So I have negative 3y cubed. I'll start with the highest degree term and work my way down. Plus 3y squared. Minus y squared. And plus y. Plus 4y. And minus 4. And again, I see now that I can regroup how I like. I can consider these two y squared terms, they're like terms. And I can consider these two y to the first power terms, they're also like terms. So I can simplify each of those. The negative 3y cubed, nothing really to do there. But 3y squared minus y squared, they're like terms. I add the coefficients. 3 minus 1 is 2. Y plus 4y, also like terms. Same variable y to the same power, the first power. I add the coefficients. 1 plus 4 is 5. And then minus 4. And at this point, I have no more like terms. I do have the same variable everywhere I see a variable, but the powers are different between all of the terms. Okay, so take a few minutes, maybe about probably about 3.5 minutes or so for this one. Work through this problem, this binomial times polynomial. As always, if you finish early, you can work ahead and start looking at the next one. If you don't quite make it all the way through in 3.5 minutes, that's okay. Again, we're just learning this, so if you're not um, super quick at it yet, that's not a big deal. But take about 3.5 minutes, work through this problem, and then we'll come back and discuss it. Okay, we're right at about 3.5 minutes. So again, I chose to think of my 3y minus 5 as kind of the one piece that I'm distributing into the polynomial. If you did it the other way, that's fine. If you distributed the polynomial into the 3y minus 5, you could do that way as well. When I distribute it, I get 3y minus 5 times 2y squared. And I kind of saw from the previous example I did, I want to avoid, say, like putting a minus here. That's a bit cumbersome to deal with later on. So here I just chose to think of it a little bit differently as a 3y minus 5 times a negative y, and then added. So that's a little bit of a shortcut that we can do if we plan ahead, if we strategize a little bit and say, oh, if I put a minus sign here, that's going to be a hassle to deal with later on. I'll just keep the minus sign attached to the y. What am I really doing here? I'm just kind of rethinking of this term, if I can select it without getting on the stuff I drew, but I'm just thinking of that minus y as plus a negative y. And then similarly, the minus 1 is plus a negative 1, which is now hidden behind all of my scribblings. So I'm just choosing to think of that minus y as plus a negative y, that minus 1 as plus a negative 1. So that's what I'm doing here. Again, if you, if this doesn't make sense, then just do it the previous way. And then when you get your, minus a bunch of stuff you have to distribute, just shuffle around as needed. You use the commutative property, rearrange some things like we did before. But if we're thinking ahead a little bit, we know that that's going to be troublesome. We can do our initial distributive property a little bit differently. So distributing 3y minus 5 to the negative y and to the negative 1. And then we do 3 more distributive properties to distribute each of these bits into the 3y minus 5. This first term out here, we have 3 times 2 is 6. Y times y squared is y cubed. Minus 10y squared, just multiplying the constants here. 3 times minus 5 is minus 15y. Again, just the constants that get multiplied there. Minus 5 times negative y, that's a plus 5y. 3y times minus 1 is just the minus 3y. And then plus a negative 5 times negative 1 is plus 5. And I made an error here. What did I mess up? I made a mistake when I was copying down. This term here should be negative y times 3y. And I had just looked at the previous line wrong and copied down to negative 5 times 3y. So I made a little mistake there. How did I realize that I made that kind of a mistake? Well, one thing that we see in math is often about patterns, pattern recognition. And I know in my previous example in the lecture, I had one factor that was a polynomial, like a y squared, a y, and a constant term. The other was a binomial with a y to the first and a constant term. And I kind of had 2 y to the first terms and 2 y squared terms that combined together. And then I had 1 y cubed term and 1 constant term that didn't combine with anything else. How did I realize I made this mistake here? Well, I kind of realized, oh, I copied something down wrong because this doesn't look like a normal pattern that I would expect from this kind of a problem. It seems strange that I get 3 terms with y to the first power in it and nothing else combines together. Now, I mean, to be fair, if something seems strange, I mean, sometimes that's just the way that it ends up. Maybe this is a type of problem that doesn't fit the pattern that you expected it to fit, and it is what it is. But it seemed a bit strange, so it made me think, okay, maybe let me just check my work here. Let me see if I made a mistake somewhere. And indeed, I did find a mistake. Tracking it through, that was what led to this negative 15y originally. So that needs to be updated to what? 3 times y times negative y is negative 3y squared. And now I do see that I have 2y squared terms that combine together, 2y to the first terms that combine together, a y cubed term, and a constant term that don't have any other like terms. They don't combine with anything. And this is more the pattern that I would expect. So once you go through several of these problems, you start to recognize the patterns, and then maybe recognize when something doesn't quite look right, and then maybe go back and just check our work. And as an aside, when I'm going through here, you should check my work as well. So when I'm going through line by line and saying that this is the answer, you should be checking and saying, is that actually right? If you were coming up with that line, is that the line you would have written down as well? But I have 6y cubed. My y squared terms, these are like terms. I add the coefficients. Negative 10 minus 3 is negative 13 y squared. My y to the first terms, I add the coefficients. 5 minus 3 is 2. And then plus 5, the constant at the end, doesn't combine with anything else. So that's this this problem multiplied out and simplified as much as we can simplify it. Okay, so let's look quickly then at special products. And again, this is kind of a smaller section. It deals with a couple special cases that turn out somewhat nicely in polynomial multiplication. So the first one, let's look at, for example, this 1 minus y times 1 plus y. If I want to multiply this out, this is binomial times binomial. I could FOIL it. I could multiply the firsts, 1 times 1. The outers, plus 1 times y. The inners, minus y times 1. And the last, minus y times y, or minus y squared. Now when I go to combine like terms, I see that my y to the first powers are like terms. If I if I think of adding the coefficients, plus 1 minus 1, 0, or if I just look at, I get plus y minus y, they go away, they cancel out. So my y to the first terms cancel, they disappear. Kind of more generally, if I had, say, a minus b times a plus b, this is what we sometimes call the cross term. The outers and the inners will also disappear. So it wasn't something special with 1 and y that made this work. Here, my firsts are a times a, or a squared. My inners are negative ba. My outers are plus ba, or plus ab. Same thing as plus ba. And then my lasts are minus b squared. Remember, ab is the same thing as b times a. So the minus ba and the plus ab, those are like terms. We have the same variables, a and b, to the same powers. Both of them are to the first power. So these middle terms cancel out. So anytime that I have a binomial where I have two terms connected by, say, a plus sign, multiplied by a binomial with those same two terms connected by a minus sign, I always end up with this kind of a pattern here, this difference of squares. So where I have something squared minus something else squared. 1 minus y squared is actually a difference of squares because 1 is the same as 1 squared. And we could actually see that this one up here came from multiplying 1 times 1. So that's really where that square comes from. When we simplify it, we don't write 1 squared, we just write 1, but kind of in the back of our minds, we know that 1 is a square. It's a perfect square. The same way that 4 or 9 or 16 are also perfect squares. So this is the difference of squares pattern. When I multiply two binomials with the same two terms, but one is connected with a plus and one with a minus, then I always end up with this pattern, the difference of squares. Where is this important? You know, why do we care about pointing out this special case? It seems like, well, I could just FOIL it. Well, that's true. But at some point, we're going to want to go backwards. We're going to want to say, okay, if you give me the right-hand side, can I figure out how it factors? Can I figure out what the component binomials are? And that's when it's going to be important to be able to recognize, oh, this is a difference of two squares. That makes my factoring job much easier. So we're just taking note of this special pattern because in the next chapter, when we get to factoring, it's going to be super helpful. Here you might say, okay, it's of marginal interest. Cool, the cross terms cancel out. But when we want to go the other way in chapter 7, when we're in factoring, this will be really nice, a really helpful thing to remember. And then similarly, if we have a binomial squared, what does that look like? We might be tempted to write something like x squared plus 4, but this wouldn't be correct. Remember, we have order of operations, parentheses, exponents and roots, multiplication, division, addition, subtraction, PEMDAS. And our distributive property takes us one level down on the PEMDAS chart. So multiplication can distribute into addition or subtraction. Exponents can distribute into multiplication. In other words, a times b to the c power is a to the c times b to the c. So exponents right distribute into, say, multiplication. That was a property we had talked about in a previous lecture. But if we did this, we would be trying to distribute an exponent into an addition. We'd be trying to go 2 levels down PEMDAS. That's not what the distributive property does. The distributive property takes us 1 level, not 2. So we don't want to make that mistake. We don't want to get overzealous with the distributive property and try to use it everywhere. Like they say, to a hammer, everything looks like a nail, right? Like we have the distributive property. It's super useful. I like the distributive property, but it's not the way to go here, at least not for the first step. So what can I do then? Well, I can ask myself, okay, what is something squared? What does that really mean? It means the thing multiplied by itself. Okay. So x plus 2 squared really just means x plus 2 times x plus 2. okay, and I know how to multiply binomial times binomial. I can use the distributive property, I can FOIL. In this case, I'll FOIL. I multiply my firsts, x times x is x squared. My outers plus 2x. My inners plus 2x. And my last plus 2 squared. Or I end up with x squared plus 2x is plus twice 2x plus 2 squared. And this seems like a bit of a goofy way to write it. If we wanted to simplify, if that was our real end goal here, we would go one step more. And we would get this as our simplest form. But the reason that I wrote that intermediate step was this pattern where we see a square and another square, and then a cross term, as we sometimes call it, a middle term, that's 2 times something, and that something is the thing being squared times the other thing being squared. This is the general pattern that we see from a perfect square binomial. What do I mean by that? Say a plus b squared. Let's see what we get in terms of a and b. Again, we write out a plus b times a plus b. When we FOIL, our firsts give us a squared. Outside gives us plus ab. Inside plus ba, which remember is the same as ab. And our last to give us b squared. So plus ab, and this is the same, this is also ab, so plus another ab. So again, I see this pattern coming from a perfect square binomial. Right, I did get something like x squared plus 4 if I had naively tried to use the distributive property here. I do get something like a squared plus b squared, but I also get this cross term, this 2ab. And again, is that super helpful in chapter 6? Maybe not super helpful. But when we get to chapter 7, when we're looking to factor, we're looking to go the other way, recognizing that, hey, I think this is a pattern that I have seen before. I see some perfect squares floating around. That might lead you down the road to say, okay, maybe this is a perfect square binomial. Maybe it's going to factor like this. Maybe if we try to kind of undo this multiplication that we did here, if I just gave you this right-hand side, maybe it'll make recovering the left-hand side easier if we can recognize this pattern. So that's really what section 6.4 on special products is about. So let's do a couple of practice problems. So take a look at these two problems. Oh, is that exactly the same one? Okay, I don't know, it's not. For some reason in my mind, I thought I had written the exact same one down here, but this is close to the one we just did that was the difference of, or the perfect square. Okay, so take a look at these two problems. Take about, let's say, 4 minutes to work through it. That'll take us up to 9:30. I think that'll be a good time to move on to the next section. Take about 4 minutes to work through these two. That might be a little bit ambitious of an amount of time for two problems, but get as far as you can, and then we will come back together and discuss. Okay, let's work through these. So x minus 2 times x plus 2, we FOIL out. We see we multiply the first, the outers, the inners, and the lasts. And again, these cross terms, these x to the first power terms cancel. We're left with x squared minus 4. We recognize this as a binomial with the same two terms multiplied by another binomial with those same two terms, where one is connected with a plus and one with a minus. And that gives us the difference of two squares pattern. X squared minus 2 squared. So if we wanted to, if we recognize this pattern, we could cut out the foiling step and just go right to the answer. I recognize that it's a binomial times a binomial. Same two terms in each binomial. One has a plus sign, one has a minus sign. So their product is going to be this difference of two squares. And then down below, again, we could write this out in FOIL, but I recognize that really this is a binomial times a binomial with the same two terms where they both have the same sign, right? So up here, we switch sign going from one to the other. Down here, we keep the same sign going from one to another. And we see that this follows the perfect square binomial pattern. We take the square of the first plus the square of the second one, and then twice, first times the second. And then the sign on that middle term is the same as the sign connecting the two in the binomial. So we could get these answers either by foiling or using the distributive property, or we could get them by recognizing that special pattern. And again, in chapter 6, is it super helpful to recognize this pattern? Not really. It's also a little bit more difficult to recognize this pattern at this point because we're still, again, getting kind of used to doing algebra and polynomials. But in chapter 7, the next chapter, it will be really helpful to recognize these right-hand sides, and especially, say, recognizing this and seeing that that's a difference of two squares. That'll be very helpful. And recognizing something like this can at times be helpful in factoring. Okay, so let's go to the next section then, 6.5, dividing monomials. And let's look at a couple of warm-up problems. So what if I wanted to simplify 16 divided by 4? I mean, I guess technically we could think of this as dividing two monomials, but it's just really dividing two numbers. If I wanted to simplify 16 over 4, and maybe you know what the answer is right away, I picked a simple problem to keep it simple. But if we wanted to go through a process, what we would say is, okay, can I find a common factor between the numerator and denominator? And I might see that a common prime factor is 2. So I could think of my numerator as being 8 times 2. And my denominator as being 2 times 2. And then I could divide out the 2's between the numerator and denominator. So 16 over 4 is the same as 8 over 2. And then I could repeat the process. Do I see another common factor between the numerator and denominator? Well, 8 is 4 times 2. And in the denominator, sometimes what I like to do is I like to write maybe a 1 times 2 so that I can divide these out, and I get 4 over 1, which is 4. Okay. Sometimes if I don't write the 1 explicitly and we cancel the 2 in the bottom, sometimes folks get tripped up and they're not exactly sure what to do with that, but we remember that there's always kind of, we can always multiply by a 1 if we need to, and that gives us something to kind of act as a placeholder for our denominator. Okay, so what if I, instead of having 16/4, which would be 2 to the 4th over 2 squared, what if I had x to the 4th over x squared? Could I simplify that in a similar manner? I suppose I could. I could say x to the 4th is x cubed times x. This is just using our product rule in reverse. I know this is true because x to the third times x, that's x to the third times x to the first, same base. I add the powers, 3 plus 1 is 4. So I could split x to the 4th up this way if I chose to. And x squared, similarly, I could write as x times x. And I see that I could divide out a factor of x from the numerator and denominator. Do I have any other common factors? Well, I suppose I could split another factor of x off of the cubed. I have an x on the denominator. I know that looking ahead to the next step, my goal is to divide out the x in the numerator and the x in the denominator. So I'll put kind of a 1 down here just to act as a placeholder. And then when I divide these out, I get x squared over 1, or just x squared. So here I started off by just dividing out one factor of x and another factor of x. Could I have gotten a little greedier? Could I have tried to split off an entire x squared from the numerator? So x to the 4th is going to be x squared times x squared over 1 times x squared, and then I could divide out the whole x squared. I could have saved myself a bit of work doing that, right? Or what does this have the effect of doing? Well, the 2 powers in the denominator just reduce the number of factors in the numerator by 2, because it forced a splitting off of 2 powers from the numerator, and then they divide it out. So could I say that maybe x to the a over x to the b equals x to the power a minus b? I have a division property that kind of sits side by side with my multiplication property. Right, x to the a times x to the b, I add the powers. X to the a divided by x to the b, I subtract the powers. So multiplying factors like this together means the powers add, the powers kind of combine in a reinforcing way. Dividing factors like this, x to the a over x to the b, means the powers subtract. So what if I had, say, 3 over 27? I could do this the long way. I could say this is, what, 1 times 3 over 9 times 3, or 1/9. Or I could try to use my power property above. This is 3 to the first power over 3 to the third, which would be 3 to the 1 minus 3 power. Or that's 3 to the minus 2 power. But a negative power, so a to the negative 1, is 1 over that. It's 1 over a. So this is 1 over 3 squared. or 1/9. Now, using the power property for this particular problem, for an arithmetic problem, it's kind of overkill, right? It took me a lot more effort to get this answer in the type of problem where I could just get the answer by easily dividing out. But if I had a problem like this, y cubed over y to the 7, maybe this works a little nicer, right? Y to the power 3 minus 7, y to the -4 power, or 1 over y to the 4th power. Okay, so when I'm dividing a monomial by a monomial, I want to keep this power in mind, or this property in mind. That when I'm dividing power functions like this, x to the a over x to the b, I subtract the powers. Now let's take a look at an interesting special case. So let's consider, before we introduce variables or any of that, just something like 3 over 3. On one hand, of course, we know this equals 1, right? On the other hand, I suppose if I really wanted to force the issue, I could think of these as powers, like 3 to the 1st over 3 to the 1st. But I would say from my property up here, I have the same base, and I subtract the exponents. So I could think of 3/3 in two different ways. I could think of it as just being 1 because that's kind of obviously what it means. But I could also think of it as being 3 to the 0 power. I start with 1 power on top, and then I, in a sense, take away 1 power from the one that's on the denominator, and I'm left with a net of 0 powers of 3. So what does it mean when something is raised to the 0 power? It means it's equal to 1. Does it change if we have variables? Not really. X over x, if I have a number over the same number, that's equal to 1 regardless of what number it is. And then similarly, we can use our quotient of powers property. And we can say this is x to the 1 over x to the 1, or x to the 1 minus 1, x to the 0. So x to the 0 is 1. Now we do have a little detail that we want to be careful of. We probably should include the special case or the exception that x is not 0. We don't want to divide by 0. We're dealing with quotients here with divisions, and we just want to make sure we're not dividing by 0. So I'll put that special case in here. I don't have to write it explicitly here because, well, 1 over y to the 4, this implies y isn't 0. Right, but if I say x to the 0 equals 1, I probably have to explicitly say that x shouldn't be 0 in that case. Up here, when I simplify, what was obvious originally that x couldn't be 0 because that would put a 0 in the denominator. But I probably ought to say over here, x is not 0. Because if I just look at x squared, it's not clear that x can't be 0. If I'm going to say these two things are equal to one another, so whether it's this one or this one that I'm looking at, if I'm going to say they're equal to one another, they have to have the same available inputs as well. If I could plug x equals 0 into the right-hand side, but not the left-hand side, then they wouldn't truly be equal. That's a little bit of a side point that is going to become a bigger deal later on in the course, but Just to kind of point it out now to be careful about things. So for instance, what's 3 to the 0? That's just 1. What is x to the 0? That's 1, so long as x is not 0. So there's kind of a rough saying, anything to the 0 power is 1. Okay, so what about so just as kind of a reminder, a warm-up before we get to the next problem, what about something like 2/3 to the 4th? How would we simplify that? We're not going to use this quotient property quite yet, but how would we simplify this just as a reminder? If I have a over b to the c power, this is a to the c over b to the c. Why is that? Well, I could think of like 2/3 to the 4th as 2/3 multiplied by 2/3 3 more times. But if I have fractions that are multiplied together, I can just kind of combine them as one single fraction. Very important. This works when they're multiplied together. If I had fractions added together, we wouldn't add the numerators and add the denominators. But because they're multiplied, this is how it works. This is 2 to the 4th over 3 to the 4th. So just remember this property from a couple sections ago. And then let's come down and look at this example. So again, this is an example where we're combining a couple of different properties. That makes it a little more challenging. We just have to be careful to use our properties correctly. Now, I suppose I could, if I wanted to, apply this property first and kind of, in a sense, distribute the exponent into the quotient. But this stuff inside the parentheses is pretty complicated looking. If I go distributing the exponent in here first, what will I have done? Well, I already have a pretty complex problem, and I'll have increased complexity, and then I'll try to simplify on the other side. It'll be a lot more difficult to simplify. I'd rather simplify first, distribute, and then simplify again. I want to manage the complexity. I want to simplify as much as I can inside the parentheses before I go and apply any other property. So I don't want to do this first. I'm going to first look inside the parentheses. Well, if I look at r squared s cubed over rs squared, remember, I have this property of multiplying fractions. If I have a product of two fractions, I can multiply the numerators, multiply the denominators, but I could also go the other way. I could split this into the product of two fractions, one with r and one with s. Now in the first fraction, I have r to the second power over r to the first power. I remember my property that here I'm going to subtract the powers. So this is going to be r to the 2 minus 1 power, or just r to the 1 power, or just r. And similarly with this s factor, or with this s fraction here, I have s cubed over s squared, s to the third power over s to the second. And that's going to leave me with s to the 3 minus 2 power, or s to the first power. So all of this stuff inside the parentheses just simplifies to r times s. So I've simplified a whole lot inside the parentheses before distributing this power of 3. The other thing that I might remember is from a previous section is the product to a power property, this essentially distributive property. A times b cubed is a cubed times b cubed. So we have a similar property for quotients and products here. So this would simplify to r cubed times s cubed. And because I started with a factor of r and a factor of s on the bottom, I probably want to say explicitly that neither r nor s can be 0. So let's do a couple of practice problems on dividing monomials. Well, dividing monomials by monomials. So let's work on these 4 problems first. And these should go pretty quickly. So I'll give you a minute or so, maybe 90 seconds for these 4 problems. So take about 90 seconds, work through these 4, and then we'll discuss. Okay, so these should have went by fairly quickly. P to the 5th over P to the 9th power. Again, just using our property, that's P to the power 5 minus 9, or P to the negative 4 power. And I know that that negative sign on the power just flips whether we're in the numerator or denominator. So P to the negative 4 power is 1 over P to the 4th power. And that's our answer. Going all the way to the bottom, y to the 0 is 1, so long as y is not 0. What about these two, though? Negative 12 to the 0 versus parentheses negative 12 and parentheses to the 0 power. The first one is negative 1. The second one is positive 1. Why is that? This is a notation issue. It's a question of what do we mean when we put a negative in front of a number? Or kind of what order do we do things? Something like negative 12 to the 0, we kind of think of this as negative 1 times 12 to the 0. So it's negative of some number. What number are we taking the negative of? 12 to the 0. 12 to the 0 is 1, and then we negate that to get a negative 1. Where down here, parentheses negative 12 to the 0 power means basically we have something like negative 1 times 12 all to the 0 power. And if we really wanted to really push the issue, we could think of using that distributive property for exponents. and we would get a 1 here. So what number are we raising to the 0 power? The full number, -12. So we just have to be a little bit careful when we have negative signs and numbers to powers. The power gets done before the negation, unless, of course, parentheses change that natural ordering. Okay, then let's work through these next two. We'll take maybe about 2 minutes to go through this one and then discuss. Again, these should go pretty quickly. The first one especially, and then the second one, just simplify the inside before distributing the power. So take about 2 minutes, work through these two, and then we'll discuss. Okay, so 3/5 3/5 to the third 3/5 to the third power. We would distribute our power into the quotient to get 3 cubed over 5 cubed. And we could leave it at that. Or if we wanted to, we could multiply it out as 27 over 125. Either way is fine for this problem anyway. If it was on WebAssign, put the answer in the way that it tells you to. And then the second problem was really the challenging one. So here we have a big complicated quotient to a power. Again, we could, I suppose, distribute the power first, but that would drastically increase the complexity, and then we'd have to do a lot of work to get ourselves back down the other side. Let's try to reduce the complexity first. If I look at what's inside the parentheses, can I simplify that? X cubed y over xy squared. Yeah, if I break this apart into a fraction dealing with the x's times a fraction dealing with the y's, I notice that each of those will simplify. X cubed over x gives me x to the power 3 minus 1, or x squared. Y over y squared, that's y to the power 1 minus 2, or y to the -1 power. The y to the -1 power becomes a 1 over y multiplied by the x squared over y. So this whole inside of the parentheses here just simplifies down to x squared divided by y. And that quotient is raised to the 5th power. Now I can distribute the power into the quotient like I did in the warm-up problem up here. My numerator is x squared, and that gets raised to the 5th power. My denominator is y, and that gets raised to the fifth power. That's just y to the fifth. And then remember that power to a power we just multiply the powers. So knowing all of these properties is quite important for working with these monomials and polynomials and so on. Having these properties right at our fingertips is super important. If you're struggling to remember all of these properties, the power to the power and the distributive properties and all of these kind of things, just maybe write them on some note cards and have them available, or just, flip through them every once in a while and review them, or have a formula sheet next to you that you can pretty quickly reference and look these up. And then, it's one of those things that after you've used the property 10 or 20 times, it's much easier to remember, right? It's difficult to remember if you've just seen me say it in class a couple of times. It's easy to remember whenever you've used it yourself 10 or 20 times, and it just sticks a little bit better that way. Okay, so lastly, we're going to start into section 6.6, dividing polynomials. And we're not going to get all the way through the section. We'll leave the last half or so of the section for after break. But we're going to start the section. So let's start with kind of a warm-up, something like a toy example, an example that doesn't make a lot of sense to actually do and practice, but that we're going to do just as kind of just to demonstrate a property. So let's suppose we wanted to do 18 divided by 2. I wanted to figure out what this is. Well, of course, we could just figure it out that it's 9. But we could take another approach. I'm not saying this would be a good approach arithmetically, but just saying that it's possible to do this. We could split this apart as, say, something like 10 plus 8 over 2. Or we might even be a little more pedantic and say something like 1 times 10 plus 8 over 2. So if I wanted to really carefully split apart the different powers of 10, then maybe I could write it this way. Now, what could I do here? I could split this fraction into 2 fractions. Remember, if we add 2 fractions with the same denominator, we add the numerators and we keep the denominator. So I have 1 times 10 over 2 plus 8 over 2. And then I might look at each of these and decide, do I have any common factors? Sure, a 5, or a 2 cancels from the 10 and leaves me with a 5. A 2 cancels with one of the 2's and the 8, leaves me with a 4. And this gets me 9, which is what I was looking for.
I have a quick question.
Yeah.
Why did you put the 1 in front of the 10? Is that necessary?
It's not strictly necessary, but trying to make it look a little more like what we'll see down here.
Okay.
Yeah.
Heard. Thank you.
Yeah, definitely. Yeah, so when we think of a multi-digit number like 132, we can think of this as like 1 times 100 plus 3 times 10 plus 2. And this has kind of the feel of a polynomial, right? This might be like 1x squared plus 3x plus 2, where x equals 10. So just so that it has a little bit more of that feel. Yeah, again, this is kind of a toy problem. It's a goofy thing. We wouldn't normally do this, but just to demonstrate how the properties could work. If I applied the same process of going through those properties to a problem like this, 15x squared plus 10x over 5, it looks a lot more complicated. But the kind of pattern, the structure is really the same as this one. It's just a numerator with 2 things added together, divided by a denominator with a single term, with just 1 factor. I could split it apart in a similar way. we have to be super careful with our just basic arithmetic fraction properties here. We don't want to do something like, make this like over 2 and over 3 or something. It just we don't want to misunderstand how the basic fractions, just what working with numbers work. Those same properties apply. So the same way that if I have the sum of two fractions with a common denominator, I add the numerators, keep the same denominator. Breaking it apart follows that same rule, just in reverse. I break the numerator apart, keep the same denominator in both fractions. In each of these fractions individually, I could ask, well, do I have a factor of 5 in the numerator? Well, here I actually do. I could write 15x squared as 5 times 3x squared over 5. And I could write 10x as 5 times 2x over 5. In my first fraction, I have 5 times something over 5. I have this common factor in the numerator and denominator of 5. They can divide out, leaving me with 3x squared. Similarly, in my second fraction, I have a factor of 5 in the numerator and denominator. They can divide out, leaving me with 2x. And this is what I end up with, 3x squared plus 2x. Do I have any more simplification I can do? Do I have any like terms, anything like that? Nope. So this is our answer. What would change if instead of having 15x squared plus 10x over 5, if I had 15x squared plus 10x over x? Not a whole lot, right? Again, this x is just kind of a placeholder. It's just a placeholder for a number. So this same fraction property still holds. I can break this into two fractions, keeping that same denominator in both. In each fraction, I can ask, is there a common factor between the numerator and denominator? Yeah, it looks like in the first one, I have x squared over x. I could either think of dividing out, or I could think of using my quotient property, using x squared over x to the first as x to the 2 minus 1, or x to the first power, or I could think of dividing out 1 power of x from the top and the bottom. Either way, I'm left with 15x to the first power. And then over here, 10 times x over x, I could either think of dividing out the single factor of x from both the numerator and denominator, leaving me with just a 10. Or I could think of this being x to the first over x to the first, x to the 1 minus 1 power, x to the 0 power, which is just 1. And then one little minor detail is I notice an x in the denominator in the original problem statement. That implies that I can't be substituting in x equals 0. So I'll just make a little note of that at the end here. And then what if I had something like this? This will be the last problem we work through today. But what if I had a problem like this, 15x squared plus 10x over something a little more complicated, but still only one term, over 5x? Does that change how we would split apart the fraction? Well, no, it really doesn't. And split apart the numerators and keep the same denominator in both fractions. Same pattern as all of the previous ones, right? It's starting to look a little bit more complicated, but we're just following the same rules. Now in the denominator, I have a couple of factors. I have a factor of 5 and a factor of x. This factor of 5 cancels with or divides out one of the factors of 5 and the 15, leaving me with a 3. And then x squared over x leaves me with an x to the first. again, either by just dividing out a factor or by using my quotient property. And then similarly in the second fraction, the factor of 5 in the denominator divides with a factor of 5 in the 10, leaving me with just the remaining factor of 2. And x over x is 1. It's x to the 0 power, it's 1. X can't be 0 again because of this initial problem statement. And so this is what we'll build off of next time when we come back. And then we'll move into what happens, how do things change, and they do change substantially. How do things change if we have a binomial in the denominator instead of a 5x, like a 5x plus 1 or something like that? And that is a pretty substantial change. So sometimes things look a little more complicated, but it's not that big of a change. Sometimes things look a little more complicated and it is a big change. And we'll see that that really is kind of a shift in gears. If we have a binomial in the denominator where we have 2 terms in the denominator, that's a different approach. Okay, I'll stop the recording.